Out here in Arizona, we really only have two seasons, really hot and nice and cool. And I'm thankful to report we're just now entering the nice and cool phase, which means at the end of every workday, I usually grab all my kids and we go for a walk on what we call the duck route. It's about a mile loop that ends into this big grassy field. It kind of slopes down like this into a wash, and there's, in the wash is a little cement thing to where if it ever does rain in Arizona, all that rainwater drains into what we call the duck pond, and that's where all the ducks are sitting there. And usually my wife and I will sit on this hill under a tree and, chat while the kids are playing ball or doing whatever. So just the other day, I had this brilliant idea. I'm sitting there next to my wife watching the kids play, and I see this hill, and it suddenly hits me. I go, Sue, I remember when I was a kid, I went to a school that had a hill like this, and we, on recess, would go out, and we'd lay down and just roll down this hill. And I go, this is the spontaneous mind of Jeremy. I go, kids, come here, check this out. And so I come over there, and I lay down, like a sausage. I put my hands by my side, and I go, I'm going to roll down this hill. This is going to be fun. And so I turn, and I just start rolling. And it was the most painful thing ever. I'm just, and my face is smashing the ground as I'm rolling down this hill. At the bottom, the kids are like, yay, Daddy. And my wife is just cracking up. I've got cuts all over my face from just smashing against the ground. She goes, well, when you were a kid, you were probably smart and crossed your hands over your chest or something. And I go, that's what I forgot. Notice what an introduction, right? That is exactly what I feel like every single time I step back into IPv6. There's so much in the world, and let me specify, so much in the United States that is still IPv4 today, that every time I get back into IPv6, I feel like I'm just smashing my face on the ground. I'm like, what was that? Oh yeah. So that's what this nugget is all about. Really, you can see I've got RIP Next Generation, but the core of this nugget is on IPv6 review, just to get us, to teach us to cross our hands across our chest as we get into IPv6 and avoid some of the silly mistakes that can cost us a lot of time, both on the exam and as we're starting to get into the live configuration of IPv6. Here are your Do I Know This Already questions, so pause the nugget, read through them. If you know the answers, you can likely move on to the next nugget in the series. Otherwise, let's get started. Well, let's get into our rocket ship and do a flyby of the IPv6 galaxy as we review the type of communication and addresses. Unicast messaging, one-to-one, as it always has been in IPv4 and now in IPv6. When one device wants to talk to another, you use a unicast message. Multicast is now a staple communication, whereas in IPv4 it's kind of like a, ooh, that's a neat trick kind of thing. Now everything uses multicast because it really has replaced the broadcast. You know that there is no broadcast in the IPv6 world, but multicast can do the same thing. There is a multicast address that your devices can use to specifically send a message to all devices on the local subnet. And I'm trying to think of a good way, because some people might just say, oh, well, then IPv6 really has broadcast. It's just they call it a multicast. No, it's kind of, the way I see it is broadcasts were just sloppy. I think of like a stockroom trading floor, in the 1970s, 80s, that kind of time frame where everybody's sitting on the floor. They're like, I'll take 50. Everybody's yelling at the same time. Okay, 50. It's like an auction. There you go, right? It's like an auction where everybody's yelling, I want that, $50, $100, all that kind of stuff. That's the broadcast world. So multicast, when it comes to IPv6, can do the same thing, but it's intentional. So I think of multicast style broadcasting as somebody standing up in a busy room and going, okay, everybody, hang on one second. Everybody, listen to me. I have this to say. Right? It's more of an intentional step. So they've reworked the multicast to have, for instance, DHCP requests be more intentional, to where just the DHCP servers get them. They've reworked the multicast to where routing updates go to just the routers, not every device. So again, by using multicast as a staple communication, you eliminate the sloppy broadcasting. If that makes sense, to where that most of the devices don't care about that, but broadcast is the only kind of communication you have. Now we have the ability to define these multicast groups to be very intentional with the way that we communicate, right? So when somebody does send a message to everybody on the subnet, it was by intention, it's by design, that kind of thing. Okay. Anycast, this is a fun new one. Anycast actually was around in the IPv4 world, but wasn't as tightly defined as it is in IPv6. Anycast is one to the closest. So the best example I can give of this is how it's being used in the IPv4 world with DNS. For instance, Amazon Web Services uses Anycast-based DNS. So essentially you assign many DNS servers in the world the same IP address, which I know within the IPv4 core of your soul is like, you can't do that. Well, yes, you can. You can actually assign that same address to multiple devices around the world, then use BGP to find the closest, because BGP can have duplicate routes all over the place in the internet. That's why the internet is so redundant and resilient in types of failure. So when I'm sitting here in South America, and I do a DNS lookup, it's going to find via BGP the closest DNS server to me and give me the best turnaround response time, right? So that's what an anycast is. Now we get to the types of addresses. In the IPv4 world, we're used to having one address, and it's kind of an anomaly or weird if we have more than one address, right? So now in the IPv6 world, it's the norm. Everybody gets a link local scope address, which is very similar to the 169.254 addresses of IPv4, those auto-generated addresses that just allow local communication. Now, the beauty of this is you have a very specific defined private address that is used just for communicating with your peers on the subnet. It's used for a lot of the routing updates and things like that, peer relationships, without having to use a global public address. And actually, let me just jump down there. The global scope address, that's your internet address, and everybody will have at least one global scope address. I've got specific slides on each one of these, so I'm not going to go in too much depth here, but this is your public address that you use. The one that's caused the most controversy is this one. The reason I say controversy is if you look at the RFC standard history of IPv6, this unique or site local scope address has been added and removed and added and removed. Essentially, people are saying, you know what, with all these new addressing types, why do you need a private address? And that's, by the way, what this really is, a private address that just works inside of the organization. Well, if you do your setup right, you can use the global address for that, or a link local address for communication on the local subnet. So this became one of those, why would you do it? But people are so used to it that they keep wanting to add it back in. So as of right now, today, as I approach 2015, this is the current standard that we have, is site local addresses are in the RFC. But tomorrow, they may not be. Well, as promised, let's dive deeper into some of those addressing types and look at the particulars. Link local addresses, I mentioned on the previous slide, were just like the 169.254 because they are automatically generated as you boot an IPv6 host, in addition to, not instead of, like it was in the IPv4 world where this meant a broken DHCP server. It is in addition to the normal, the global address that the host uses. You can identify these guys by the first 4 characters are always FE80. If you see that in hex, that's what it looks like. If you look in binary, that's the binary equivalent, followed by 54 bits of zeros, which result in the address looking like this. You might remember in the IPv6 world, the double colon equals a row of consecutive zeros. So you can see right here, the first 64 bits of the address in IPv6 is actually FE80, followed by the auto-generated portion, or some people will call it the EUI64 generated address. What is that? That is taking the MAC address of the host, right, whatever the MAC address is of the interface that's getting this link local address, and splitting it right down the middle. It's so weird how they did this. They said, okay, if this is your MAC address, let's take this portion, move it to the left. Let's take this portion right here, move it to the right, and squeeze in FE in the middle. Why? Because a MAC address is only 48 bits in length, and we need a 64-bit address that comprises the last 64 bits of our IPv4 auto-generated. So that's just, I'm sure there's some technical reason why it's there, but it just feels like to me they're chucking darts and they're like, oh, that landed on the FFFE square. So again, I guarantee you there's a technical reason that it's there, but that's filler. It's what extends your address to be 64 bits at the end, combining it with the first 64 bits starting with FE80, and you have a 128-bit link local address. Now let's take a look at the global address. This is the internet addresses of the future, and it really puts in perspective when you look at that first bullet just how big the IPv6 addressing space is. The RFC standards have said, you know what, just for the foreseeable future, like let's say planet Earth, let's just start off with the first 3 bits locked in on the internet addresses to be 001, which makes them look like this. And that should pretty much take care of the planet Earth. right? I mean, wow, just how many addresses are there? Now, I may eat my words in 15 years when they say, wow, who knew that that we were going to assign IP addresses to every genetic molecule of a person's body, or who knows what the future will hold. But that is considered the global prefix. And here's how this works. You've got the IETF, right? The one who's managing all these addresses, handing these out to the ISPs. And so the ISP will receive a global prefix that will be essentially 48 bits or less, right? So this will be, hey, ISP1, here's your chunk of addresses. And let's just say it's 2001:1111 :/32, right? So they get a /32 global prefix. Now it's up to that ISP to start subnetting that out and assigning it to their customers. So here's customer 1, customer 2, and so on all the way down. The ISP will say, okay, I'm going to give you these /48s or /56 or /64. But I mean, think about that. 32 remember from IPv4, how many addresses are in 32 bits? 4 billion something. Right? That's the IPv4 address space. And they're like, yeah, that'll be kind of what we give an ISP to give to their customers. So an ISP now has 4 billion addresses. Or let me even back that up. 4 billion subnets of addresses that they can give to their customers. Seriously, we're just talking about the first 64 bits of that IPv6 address. The customer can do whatever they want with that interface ID. So let's talk about a small customer. Right, from an ISP perspective, ISP 1 might say, okay, customer 1, you're like a house, so we're just going to give you 2001:1111:1112:0001, right? /64. That's one of the prefixes that we will give you. So you're kind of like from the house's perspective, you're like, oh man, I only get one subnet assigned to me. You've got 64 bits then to play with as a customer, as a house. Right, to where you can then say, you know what, 64 bits, I don't even know what that comes out to. I know 32 bits is 4 billion something. 64 bits? Hi. So I just had the thought, I'm like, I could totally use 4 billion addresses in my house. But anyway, that's what that customer gets, to where now they get one network, but they can essentially start having all these firewalls, routers, NAT addresses, all that kind of stuff, addresses within their network that uses that prefix that they've been given, that first 64 bits sitting right there. So again, puts in perspective just how many addresses there are. So global routing prefix given to the ISPs. ISPs subnet that out. So the subnet is essentially whatever is left over. So you can see if you were given a global prefix of, let's just say, 32 bits as an ISP, like I drew up right there, they will subnet it out, and their subnet ID will be essentially 64 minus that 32, the global prefix they were given. So they have 32 bits of subnetting that they can do in assigning that to the customers. The last thing I want to do in this nugget is a hands-on configuration of IPv6 and RIP next generation. You can see my base address here, 2001 DB86783X, where X is any one of the 3 subnet values representing the 3 networks that I have in that diagram. Before we go right into the configuration, though, it's worth mentioning that you'll see a lot of documentation say you should not take an IPv6 address more specific than a /64 subnet mask. Why? Reason why, the number one reason, is because it eliminates your ability to do auto configuration of your IPv6 address. Auto configuration implying that EUI 64, which allows the devices themselves to automatically generate their host portion of the address by taking their MAC address, jamming FFFE in the middle of it, and bam, pretty cool, because it eliminates the need for DHCP on our networks. Our devices can just be plug and play. You lose that ability if you go more specific than a /64, and you have to rely on something like DHCP version 6 to fill in the gap. Second reason is because it's rumored, I've never seen one, but it's rumored that there are devices out there that don't support the more specific subnet mask than a /64. That, to me, anyone remember IP subnet 0? Remember in the IPv4 world, if you ever did subnetting, the very first and the very last subnet was IP subnet 0 and subnet 1. And there were some devices that didn't support those. Well, you know what happened to those devices? They died. Nobody used them anymore. They got patched. They got upgraded to where they could support that. And that's I mean, come on. So that being said, you will still see a very common theme when you see IPv6 configurations out there where people are sticking to this /64 subnet value all over the place, right? That's kind of this is the new /24, right, of the IPv4 world. Now that I do have an exception for you, and that's WAN links. You'll see a lot of recommendations that you use a /127 subnet mask for your WAN links. That's kind of the equivalent to the /31 of the IPv4 world, where you would, let's just say, subnet 10.1.1.0 with a /31, which would say, okay, 0 and 1 is one subnet, 2 and 3 are another subnet. It's real cool, tight subnets with just 2 addresses. Now, not only is that for efficiency purposes, because, come on, I mean, throwing a /64 to WAN link, it goes against the grain of all things holy and right in IP addressing. Throwing a quadrazillion addresses at a WAN link is just not right. But the second reason why is because you now have essentially a point-to-point WAN link where there is a quadrillion addresses out there that is all considered on the same subnet, and that could open the door to denial of service attacks of those devices. So doing a /127 really pinpoints it down into a little WAN subnet. Cool. All right, with that being said, let's dive into the configuration. Here's how it goes. I'm going to start off with router 1, bring him into the picture, and right now there's nothing going on. I don't have any configuration on the interface, so I'll do a show IP interface brief. Interfaces are shut down as well. It's just a brand new router. So I've got router 1. I'm going to go into global config mode, interface 000, and I'm going to do IP, actually, hang on, whoa, hold the fold, IPv6 unicast routing. Got to be the first address I type in there. Let me just bring the bottom of this up here, because that's what turns on the ability to really even do anything with IPv6. So now we'll go into serial 0/0 IPv6 address, and we'll do 2001:DB8 :6783 :122. Now I didn't put the host addresses on there. I'm going to do a : let's just do 1 since it's router 1. We'll use kind of the router ID to come up with that, /64, and I've assigned my first IPv6 address to that device. Do a no shut, exit out of there. I'll do a show IPv6 interface brief, right? And now I can see I've got my first address up and up, or the 2 status, that's physical and data link, and look at that. It automatically generated a little link local address. How do I know? FE80. There's my MAC address split right in the middle with that FFFE. You can see right in the middle, splitting that up, and then MAC address filling in the rest of it. Okay. So let's go into fast Ethernet 0/0. No shutdown. IPv6 address 2001:DB8 :6783. You know, someday I'm going to be whining. I'm going to be like, you know, I miss the old days of my IPv4 addresses, and somebody's be like, Mister, you're old. Who knows? Yes, I do miss typing in addresses like 10.1.1. Miss, good grief, I still do it all the time. It's not gone yet. Not old yet. So let's do show IPv6 interface brief. Woo! We've got our first router. Wait, there's more. I'm going to go into global configuration. Let's do router, not just router, IPv6 router RIP. Now, notice in this RIP world, in the old IPv4 version, that's it. You type router RIP and then you type in your network statements. Not so here. I'm going to do RIPng. Now, this is case sensitive, and this is a string used to identify the process. Now, normally, again, IPv4, I'd say network 10.0.0.0 or version 2 or no auto. All that kind of stuff goes away with RIP next generation because of all the improvements they have. Actually, it's not that much better than the old RIPs, but they do improve things like going under the interface to enable it. So let's go under, let's run RIP to the internet. Why not? I'm going to do serial 0/0 and do IPv6 RIP. RIPng enable. Sweet. What I've done is I've essentially assigned the serial 0/0 interface to the RIPng RIP routing process. So this command up here that I typed in, where was I? Global config mode, right there, highlighted. That just turns RIP on. It's like a light switch. Flip. We now have this process called RIPng that I can assign my interfaces to, which I need to go into fast Ethernet 0/0 because I'm talking to the internet right now. It's not really reaching anyone with its multicast love of RIP next generation. So now it's going internal and sending out these broadcast or multicast messages, are no broadcast, to this subnet 123. All right, so let's hop over to router 2. That would be that guy. Bring him up. And I'm going to be including, if you haven't guessed, the GNS3 topology I use for this, just so you guys have a quick sandbox to play in. I believe this is in the same state. Show IP interface brief. Let's go a little quicker on this guy, right? Interface, fast IPv6, unicast routing, just like I was saying. Interface, fast 0, no shut, IPv6 address. Forgot the root. Shoot. 2001, DB8, 6783, 123, colon, let's go 2 on this guy. I did 1 on the other one, right? I think so. 64. We'll be able to test real quick. So this was fast Ethernet 0/0. Let's go to serial 0/0. Move that up a little bit. 0/0. Up arrow is my friend, and I'm going to change this to 121 as the subnet ID. No shutdown. There we go. Let's do our ping. So I'm going to do a ping. Now you can type in ping IPv6 and specify and all that, but you know what? Cisco routers are smart. You can just type in the IPv6 address, and it's cool with that. So let's do. This is where I see myself doing a lot of when we go IPv6 around the world. Copy and paste. So I'm going to do 123::1. Woo! We've got that. I'm just actually curious. I just had this thought. Sweet. So I can tell that to him. Now I haven't actually set a VTY password, so it's saying password required but none set. But just kind of fun to know that I can actually telnet to an IPv6 address. Oh, RIP. Go into global config mode. IPv6 router RIP. Name of that process RIPng. It does not have to be the same. Not rig, RIPng. It doesn't have to be the same between the routers. This is locally significant, but you do have to remember the case sensitivity of it. Interface fast Ethernet 0/0 IPv6 RIPng enable. Right, same commands. We'll go under serial 0/0. Do the same thing, and now let's check it out. Let's see if we're getting some advertisements. Show IPv6 route. Woo! Look at that. We've got our first RIP route being learned. 2001 DB8 6783 122, which is representing the subnet down here of that WAN link that it's learned about. Notice over there we still have the same old administrative distance of 120, hop count of 2. I'm going through one router to actually get there, so it's still good old RIP. But look at this. It's saying via link local address. What does that tell me? It tells me that router 1 is actually communicating, quote unquote, forming neighbors. There are no neighbors in RIP other than just somebody who happened to hear the multicast, but forming a RIP version of neighbors using link local addressing. Pretty cool. All right, let's bring router 3. This one should be the fastest router yet because we've done this a couple times. Okay, router 3. Global config mode, interface 0/0/0. Let's do no shut. Oh. I should have a script. I should, but I don't. So I'm going to do totally out of order IPv6 router RIPng. Good. Interface 0/0/0 IPv6 address. And that's where we'll use our 2001:DB8:6783:121:3/64. Again, just using the router name as just a unique identifier. No shut on there. And we'll assign this to the IPv6 RIPng enable. Good. So now, at this point, I should be able to, let's do a show IPv6 route, should be able to see the 2 different networks advertised via RIP. You can see the one furthest from me, that 122 subnet right there. Hop count of 3, so I'm going through a couple routers. This one a hop count of 2, both being advertised by the same link local address. Essentially, they're coming from router 2 as my neighbor. And I should be able to ping all the way down here to that final subnet. So let's do a trace route. Trace route IPv6. You don't have to type that in, but we'll go 2001. Ooh, hang on. No IP domain, or what? Hang on. No IP named. How come that slips my mind when I need it most? No IP domain. Look up. Because now I think in GNS3 it automatically has that command in there, but otherwise every time you do a trace route it tries to resolve every single host name along the way and just kind of hangs, which is annoying. So trace route IPv6, we'll do 2001:DB8:6783:121 122 colon 1. Nice. Fast. So we went through two different routers, 121, and that's going to be router 2, and 122, which happens to be router 1 over there to reach our final destination. It's really not that bad. Yeah? I mean, think about it. Think about, I know you're like, well, yeah, that's because I'm a CCNP level person now, but I mean, think about how hard it was in the CCNA to learn the network command and the wildcard mask and what did that mean and all that kind of stuff. I'm like, you know what, this is, to me, it just feels simpler. You go under the interface, you're like, I want that run and rip. No, I want that one too, run and rip. Okay, I'm done. You know, just kind of exchanges all the routes from there. So obviously, we're going to dive into a lot more depth, but the whole goal of this nugget was to dive back in again, so you're not rolling down that hill, smashing your face on the grass like I did. Every single time you come into IPv6, just get the gears going again. It's like, that's how it works. That's the different kind of addresses. That's how we communicate. That's the configuration. I hope this has been informative for you, and I'd like to thank you for viewing.